Welcome to all the students of the Material Science first year course. Today's chapter video will be on crystalline solids. As you are all now familiar with atomic bonding, let's take the next step and look at crystalline solids, which is the structure of how these atoms form a bigger piece of the picture in a solid material. So let's take a look at one of the most favorite materials in the world, which is a diamond. Would a diamond be so perfectly shaped if the atoms were lying around all over? No, they have to be structured in a specific manner, and that is where we get a unit cell. So if we forget about the complex structure of a diamond and look at our most basic unit cell, it would be a simple cubic. So on each of these corners in the cubic, it is actually an atom situated here, and this part would form the bond. And this is the nucleus of the atom. So to draw a bigger picture of this, this would be one of the corners of your unit cell. Now, to form a bigger part of a material such as your kitchen knife, we would have to have millions of these atoms situated all over the part of the knife's blade to actually form a solid piece of material. These unit cells then orient themselves in a structured manner called a lattice cell, which is basically just a repetition of the unit cell over a long distance. So it's important to remember that one of these blocks is called a unit cell, and all of them together in a big arrangement is called the lattice. Now each corner part is a single atom, and these atoms can form different, more complex arrangements, such as your orthorhombic, triclinic, monoclinic. But in this course, we will limit the arrangements to 4 basic ones, which is your simple cubic, as well as a face-centered cubic, where in this case there's an additional atom on each of the front planes of the unit cell. So if we just took an outside view, but if we would look at the unit cells inside, there would also be another atom at the bottom on this back faces as well. This is called the face-centered cubic. Another structure that is very commonly found is a body-centered cubic structure, which is your BCC structure. In this case, you have an additional atom which is situated right in the middle of this unit cell. Lastly, excuse this line, we have a hexagonally closed packed structure. And these form most of the common found lattice structures found in metals, which is a crystalline solid at the end of the day. So for a moment, let's go back to our simple cubic. As it is a cubic structure, the lengths are all equal. And remember, in the bigger lattice cell picture, we are actually sharing atoms with the unit cell next to it. So in the end of the day, this, in a 3-dimensional picture, only makes part 1/8 of the unit cell. To get the total number of atoms in this single unit cell, as there are 8 corners in the cube, let's complete the cube. We have 1/8 of an atom on each side, times 8 for each corner, and we only have 1 atom in a simple cubic unit cell. So just think about how small this unit cell is that actually builds up a lattice to form a bigger component. If we would then want to calculate the volume of the simple cube, we would use our volume formula, and in this case we have to take another step and remember that this atom, as I've drawn it with only a small dot, is actually just a representation of a bigger picture. So let's look at the front plane. If we draw in the atom, with this being the nucleus, the atom would, this would be the outer shell. And so we can complete the cube in a three-dimensional manner. And so forth. So here you can once again see that it's only a part of the atom that is hosted by the unit cell itself, but as it shares with the lattice. So here we can see that if we know the material, we would know that the radius of each atom, and in effect A, becomes 2r. And we can easily put that into our volume formula to get the volume of this specific unit cell. Similarly, we can do that for the FCC structure, BCC, and HCP if we know where the atoms are arranged within a simple unit cell. So let's move to the more complex situation of a FCC. I'm only drawing in the atoms on the front plane. So if we could complete this picture and draw in all the atoms, you will see that this middle atom pushed the outer atoms apart, and we can no longer rely on this equation as there's a gap in between these two atoms. Just to remember, it is still a cubic structure, so A equals to A and so forth for the length, height, and breadth. So what would we do to get a relationship between a known value, r, which is the radius of the atom, is we can look at this direction where they are closely packed, so there's no gap in between, and call this y. So we would know that y equals to, this is one radius, another one, and another one, which is 4r. As we now have a relationship for this direction, we want to get this in terms of A to complete our volume formula. So let's move over to our old friend Pythagoras. In this case, we have a solution for y, which is 4r. And we can, in this case, easily get the volume after completing A for the FCC crystal structure. So to make things a bit more complex, after solving the solution, which would be your homework for this tutorial, we will also look at the BCC structure. In this case, there's an atom situated right in the middle of the unit cell, and if we would draw this plane, you will see that these atoms are once again pushed aside to accommodate the atom in the middle of the unit cell. Let's complete it in 3 dimensions. So once again, A is equal for the length, breadth, and height because we're still dealing with a cubic structure. But in this case, we will have to make use of another direction to get the radius in terms of A. So for this tutorial class, you will have to do the volume of the BCC structure as a homework problem. I'm going to give you a hint how to solve this. Let's look at a 3-dimensional sketch. So we once again have a cubic structure, so our atoms are situated on each corner. But we now have this center atom right in the middle of the whole cube, which pushes these 4 corner atoms away. So what will we do to get a relationship between A and our radius of an atom r? As we need A in relationship to r to put A into the volume to get the volume of the BCC structure. I'm going to give you a hint on this one, and then you'll have to complete it in the test prior to entering your tutorial class. So the hint is to look at a different direction of the unit cell, which is this plane in 3 dimensions. Try to make a sketch of the front plane, the side plane, and a section cut of the BCC structure, and you will see that in this direction the atoms are closely packed, and you will get a solution for the volume.